I'm Joe Genova, and this is my Robold Physical Hands-on Circuits project. Here's a basic overview of the project. Main task here is to vary the brightness of a red LED, and we're going to do that via the use of inductors and a potentiometer. And while we're doing that, we want to mainly analyze the voltage drop across each component. Uh, Once you see the circuit, you'll see that the current actually stays the same through the entire circuit. So really the only thing we have to analyze is the voltage drop through each component. And we're going to compare that with the predicted as well as the actual values that we're able to measure. And we're going to throw in some hypothetical situations there as well. And the inspiration of this mainly comes from a website that I saw while I was researching each of the individual components that we were given. Saw something talking about inductors. They sounded pretty cool, and I wanted to kind of look into that as a bit more as a project. So the Felsted circuit will start here. This is an idealized version of our circuit. You can see the actual circuit down here in the bottom left, and I'll have a close-up photo of this later, but we have two inductors in series. Now, in Felsted, we're just going to make that one inductor with the equivalent inductance. We also have a potentiometer here. Thing about Felsted is, here's the potentiometer component. It's very hard to give precise values, so you can't just set the resistance of it that you're measuring. So what we're going to do is we're actually going to replace that just with a resistor, and we're going to measure the resistance that we're getting over the potentiometer, and we're going to plug that in as our R1 down here, and then that's just going to allow us to be more precise. It's going to help account for any errors, because as I said, you can't be very precise with the potentiometer component, so we're going to replace it with a resistor that takes the equivalent role. Here's a photo of our actual circuit. It's pretty simple, just a couple batteries. They feed in. This is a main switch here, so this one is not actually shown on the Felsted circuit because it allows me to isolate the rest of the circuit. Just makes it easier if I need to change out components, change some wiring, or if I burn out an LED, I can just replace it real easy. I don't have to pull each of these batteries out. I can just isolate the circuit. And then from here on, this would be the start of the Felsted circuit here. So you would have this switch. These are the inductors in series, potentiometer, LED, resistor, R2, and then goes back into the battery. Like I said, it's a pretty basic circuit. Calculation equations, because that potentiometer up here and resistor R2 down here are in series, we are going to add them. That's going to give us our equivalent resistance of the entire circuit. And using V equals IR, we can derive some KVL equations. We're going to have a V in over here at the battery. And then up here, we're going to subtract minus IR1 for the potentiometer. We're going to have a voltage drop over the LED. And down here, we're going to have minus IR2 for the resistor. Now, we plug that all into our final KVL equation, and we're going to have V in minus 1.8 volts equals IR1 plus 220. And the negative 1.8 here are coming from the voltage drop it's the forward voltage across the LED, and that's given from the data sheet on the LEDs. And 220 is just the resistance of the resistor that I chose. R1 and V in are going to be the two variables that change, and when those combined are going to be able to give us current. R1 is the potentiometer. As we change that, obviously our resistance is going to change, and V in is going to change as the batteries lose charge. Predicted values using V in as 4.098 volts and R1 as 95.1 ohms. We're able to plug these into KVL and get about 7.3 milliamps out of it. Something to note here is Felsted does give a slightly different number of 7.4 roughly, but this is mainly due to the differing values of the forward voltage across the LEDs. So there's a different voltage drop, which in turn is going to give you a different current value. Now with these current values, we're able to plug that in, and we can actually see the individual voltage drops across each component using V equals IR, and over like I said, over each of the individual components. Now, if we take all of those voltage drops and we combine them with 1.8, we're going to see that we get back to our original voltage, and that's good. That's a little check that we're able to run just to make sure that everything's adding up. We're not losing any voltage anywhere. Real life, however, we do have some issues. Mainly, the biggest difference that I can see from my measurements is in here in the center photo. This LED has a different forward voltage than what's actually on the data sheet, and obviously there's variance in that. So we're measuring about 1.9 volts. Because of that, we're going to have different voltage through the potentiometer and the resistor. Therefore, they are going to change a bit. So you can see these are some of the corresponding results. And I have all the math worked out, but you can see there's difference. The other thing to note is that somewhere in the circuit about 0.015 volts is dropping just throughout the circuit through the various components. It's only about 1/3% of the total voltage, so it doesn't seem of high concern, but it's something that should be noted and something that we don't see in the idealized Felsted version. And I kind of mentioned that in the comparisons here. We see this is a voltage drop outside of our potentiometer and our LED and our resistor components. And like I said, I already covered that we have a different forward voltage across the LED, and that's mainly leading to are differences in our potentiometer here in our resistor. So in conclusion, despite the slightly unknown drop in voltage, I feel like this model is pretty accurate to what we're actually modeling in Fallstead. Um, I think it's a good representation. Like I said, I don't think there's too many issues. I think everything kind of falls within what I would consider an acceptable error. However, while I met all the project requirements and I tried to keep the mindset of let's keep this simple but very accurate measurements, I really wish I could have done more. One of the first things I did with this project when I saw that website in my sources, they talked about how like when you use inductors, if you hook inductors up to an LED and you turn on the power, the inductors, because they resist current, the LED actually won't come to full brightness to start with. And I was like, wow, that sounds really cool. I want to do that. I can think of some cool uses of that, like in real life. And then I read more and I found out that you need a massive inductor, like magnitudes larger than what I had to be able to do that. So I feel like I probably didn't use the inductors as well as I could have. Um, but this is the first time I've ever done anything with wiring or circuits, so I really didn't want to overwhelm myself and get into something where, sure, I had a complicated model and it did a bunch of things, but maybe my measurements weren't accurate. So I tried to keep to the simple and accurate mindset instead. So while it's accurate, I really wish I could have done more, and I feel like the inductors probably could have been used a bit better. But with my limited experience, I didn't want to go too far. And then here are my sources. There's the website where I got kind of the inspiration from, and then obviously Top Hat and your lectures were used to help derive a lot of these equations and just kind of like the background information when wiring this. Thanks. Bye.